Hello, everybody, and welcome to a new episode of the European Young Chemist Network podcast. My name is Mark Kalada, and in today's episode, we are going to talk about the importance of the electrocatalysis for sustainable energy, focusing on water splitting. For that, we have invited Professor Kai Exner, expert on this field. Professor Exner studied chemistry at the Justus Liebig University in Gießen, Germany, and obtained his PhD for a thesis on the theoretical description of the chlorine evolution reaction over ruthenium dioxide-based electrodes in 2015. After postdoctoral stays at the universities of Ulm, Gießen, and Sofia, in 2021 he was appointed Professor of Theoretical Inorganic Chemistry at the University Duisburg-Essen in Germany. Professor Exner has received several awards and fellowships throughout his scientific career. Recently, he has been granted €1 million funding from the federal state of North Rhine-Westphalia for a project in the area of electrocatalysis relating to the topic of today's podcast.
Hello everyone! In today's episode, we are going to talk about the importance of electrocatalysis for sustainable energy, focusing on water splitting. For that, we want to warmly welcome our guest, Professor Dr. Kai Exner. Kai, welcome.
Thank you, Katarina, for the kind introduction and for the invitation to today's podcast. It's always a pleasure for me to talk about the vibrant area of electrocatalysis and the challenges in this field.
Could you shortly explain to our listeners what electrocatalysis is and why electrocatalysis is so popular nowadays?
Sure, I'm happy to introduce the listeners to the area of electrocatalysis. The word electrocatalysis consists of two components. On the one hand, electro, and on the other hand, catalysis. Let me start with the first part. Electro indicates that we refer to electrochemical processes. An electrochemical process consists of two half-cell reactions, namely the oxidation reaction taking place at the anode and the reduction reaction occurring at the cathode. Consequently, there are two electrodes, anode and cathode, immersed in an aqueous electrolyte, and the two electrodes are connected by a wire to close the electric circuit. The word electro also indicates that either we can tap a voltage between these two electrodes when the electrochemical process is occurring, or we have to apply an electrode potential because otherwise the electrochemical process at the anode and cathode does not take place. Let me give you two representative examples that are also of importance to our society. The first example refers to a fuel cell, where gaseous hydrogen and gaseous oxygen are converted into water. This process occurs spontaneously, and as such, the chemical energy stored in the reactants hydrogen and oxygen is transferred into electrical energy. Namely, we can tap a voltage between the two electrodes at anode and cathode. The second example refers to an electrolyzer. Where water is decomposed into gaseous hydrogen and gaseous oxygen, and thus we indispensably need to apply an electrode potential to make this reaction happening, thereby converting electrical energy into chemical energy, mainly stored in the hydrogen-hydrogen bond of the product gaseous hydrogen. Both fuel cells and electrolyzers are intensively investigated at the moment, particularly relating to the catalysis, which brings me to the second component of the word electrocatalysis. I explained to our listeners that there is an electrode at the anode and cathode both. Each electrode surface is commonly coated with some material, which is denoted as the electrocatalyst. The task of the electrocatalyst is to catalyze the process at the anode or cathode with highest efficiency. That is, with as few losses as possible. Regrettably, for certain electrochemical processes, the occurring losses are still somewhat too large, and the electrocatalysis community is actively working to find better catalytic materials so that these electrochemical processes can be implemented into our everyday life. For instance, the first electric vehicles based on the concept of a fuel cell are already operating.
Oh, okay, that was quite insightful, thank you. But you mentioned the losses. Could you please tell us something more about the losses? For instance, for which electrocatalytic processes are the losses particularly severe, and how is this really related with your research activities?
Yeah, thank you for the interesting question. These are important aspects to discuss. My research activities mainly refer to the electrocatalytic processes taking place in an electrolyzer, that is, the hydrogen evolution reaction at the cathode and the oxygen evolution reaction at the anode. The hydrogen evolution reaction is a simple two-electron process, but the oxygen evolution requires the transfer of 4 electrons within the reaction. As a consequence, the losses for the oxygen evolution reaction are much higher than that for the hydrogen evolution reaction, because oxygen evolution is much more difficult to catalyze. As a theoretical electrochemist, we often refer this to the number of reaction intermediates in the reaction. Due to being a simple two-electron process, the hydrogen evolution reaction requires the stabilization of a single reaction intermediate within the formation of gaseous hydrogen. However, the oxygen evolution reaction necessitates the formation of 3 reaction intermediates during the formation of gaseous oxygen. Of course, it is much more difficult to find an electrocatalyst that adequately stabilizes 3 reaction intermediates than a single reaction intermediate, as encountered for hydrogen evolution.
Oh, quite interesting, Kai. Tell us more about the discovery of suitable electrocatalyst for the oxygen evolution reaction, if it appears so difficult to find them.
So first, I should emphasize that there are different length scales on which electrocatalyst optimization is carried out. As theoretical electrochemist, I work on the atomic scale. That is, we are trying to find potential material motifs by the application of electronic structure calculations, thereby mainly focusing on absorption energies of reaction intermediates. By using dedicated evaluation schemes that are based on the traditional Sabatier principle, we can render conclusions about the suitability or non-suitability of the investigated material motif.
So, what is your main contribution to the field, and how did you advance the search of material motifs on the atomic scale?
Well, my main contribution is that I expanded the conventional Sabatier analysis, which relies on the assessment of the reaction intermediates absorption energies under equilibrium condition. I was talking about the losses before. These losses occur because every electrocatalytic process cannot be carried out under equilibrium conditions, but rather we have to apply a so-called overpotential in order to make the reaction happening. If we analyze the reaction intermediates absorption energies under reaction conditions, that is, with application of an overpotential, it turns out that the conclusions of the conventional Sabatier analysis at equilibrium do not entirely hold true anymore. For almost 2 decades, it was believed that an ideal electrocatalyst for the hydrogen evolution reaction should stabilize the reaction intermediate, absorbed hydrogen thermoneutrally under equilibrium conditions. Yet I was able to demonstrate that the ideal electrocatalyst switches from a thermoneutral to a weak binding material as soon as an overpotential is applied. This insight, meanwhile experimentally confirmed, may help us not only to overlook promising material motifs as possibly encountered with the conventional Sabatier analysis at equilibrium.
Does this mean that the main challenge in your field refers to the identification of suitable electrocatalysts for the hydrogen and oxygen evolution reactions?
Well, I would say that this is only part of a more complex problem. So far, I was referring to the Sabatier analysis, which is used for the identification of electrocatalysts. However, we should also consider the approximations in the theoretical approach to study the catalytic processes at the electrode-electrolyte interface. I was pointing out that commonly electronic structure calculations are applied, using the density functional theory approximation. This is a very popular approach, but also has some shortcomings. On the one hand, the description of the aqueous electrolyte solution and the electrode potential relies on simplified frameworks, and on the other hand, the computation of the reaction kinetics in terms of transition states is still in its infancy. For a thorough description of electrocatalytic processes, it would be required to know the entire free energy landscape consisting of reaction intermediates and transition states. As a consequence, the entire Sabatier analysis for catalyst development is an approximation per se, and it is only used because the actual reaction kinetics of electrocatalytic processes often remains unknown, and therefore we do focus on the absorption energies of reaction intermediates.
Mm-hmm. Until now, we've been talking about the atomic scale. What about the large scale, for instance, for the entire water splitting process?
Thank you for this interesting question. So some of the questions that I addressed also directly refer to the large scale. So, for instance, let me point out the chemical nature of the electrocatalyst for the hydrogen and oxygen evolution reactions. For the hydrogen evolution reaction, platinum is the most efficient electrocatalyst. However, platinum is a scarce noble metal with a price of more than 30,000 euros per kilogram, and as such, the platinum loadings at the cathode need to be reduced to a minimum in order to make platinum-based cathodes economically feasible. Nowadays, cathodes with less than 0.5 milligram platinum per square centimeter of surface area show sufficient electrocatalytic properties for the hydrogen evolution reaction. Consequently, it appears that for the hydrogen evolution reaction, platinum-based electrodes can be used as electrocatalysts even on the large scale. A different situation, however, is encountered with the oxygen evolution reaction. There, commonly, iridium-based electrodes are used as the electrocatalyst in an acidic medium. The price of iridium exceeds 40,000 euros per kilogram, but iridium is even less abundant than scarce platinum. Namely, about 4 tons of iridium are manufactured per year compared to almost 200 tons of platinum. There's a factor of 50 in between, rendering that even with extremely small iridium loadings, iridium-based anodes can never be economically feasible on the large scale. So far, no electrocatalyst could be found that is as stable as iridium-based anodes in an acidic electrolyte. A potential strategy to circumvent this is to carry out oxygen evolution reaction in an alkaline electrolyte, because for alkaline conditions, electrocatalysts based on cost-saving non-scarce metals have already been developed. The problem of alkaline conditions, however, is that alkaline electrolyzers are not able to cope with the fluctuating energy supply of renewables. As you can see, the implementation of the oxygen evolution reaction at the anode still poses huge challenges that we need to overcome in order to make the conversion of electrical energy into gaseous hydrogen economically realizable on the large scale, thereby moving toward a green energy scenario based on renewables and carbon dioxide-free energy storage.
Thank you very much, Kai, for your explanations. I think this was an excellent outlook on the lively area of electrocatalysis. We wish you all the best for your future research activities. And thank you all for listening.
Thank you, Katarina, for your kind wishes. All the best and stay healthy.
Hello, everybody. It's Mark Kilada here again. We hope you enjoyed our podcast and stay tuned for our next edition.